Really awesome to be here. So good morning. Great to be giving one of the first talks of HashiConf in this beautiful location in Napa. So my name is Tim. I'm the infrastructure engineering lead at Verizon Labs. You probably haven't heard of us. I guess in short, we don't fix your iPhone. We can't get you a cheaper calling plan, anything like that. But what I can do is I can talk to you a lot about about the things that my team have been working on in the area of infrastructure engineering. So specifically, the things I'm going to be covering a few things in this talk. I'm going to be talking to you today about providing some context about what is interesting, what's happened over the last few years in the industry, to try and give you some context about what's interesting to large companies and why is it interesting. I'm going to be talking to you about some observations we've had about how to run and build a large engineering team. And also going to be talking to you quite a bit about an internal system we built, which we affectionately call Nelson, which is our deployment and lifecycle management engine. So firstly, going to be talking to you a little bit about this, providing some context. So where are we at? What's happened in recent years, so maybe the last 5 to 3 years, that's kind of changed the way in which we look and consider software. So absolutely without a doubt, the proliferation of resource management, that's to say scheduling and placement, automatic placement within the data center has been a huge, seen a huge step forward. So obviously products like HashiCorp Nomad, Google Kubernetes, Apache Mesos, all of these projects are probably well known to many of the people here. In short, this kind of is important for two reasons. The first is that can't remember who said it, but it allows you to treat your servers like cattle, not like pets. We can stop having to provision a specific rack, specific node for a specific application. But more importantly, that enables, from a business perspective, that enables the decoupling of the data center and the application team, because when they're managing the data center, they don't then have to worry, which app is on which system, and the contract between the data center team and I guess the application and operations team changes significantly. So it commoditizes it for the data center team, so they simply don't have to care. They can just focus on basically hardware maintenance, hardware lifecycle, so on and so on, all the things that you would want them to be focusing on, as opposed to did we just cause an outage on XYZ application because we happen to lose a node in that rack. So the second thing, which is, I guess, sort of much touted, is kind of the possibility of higher utilization. So I call it possibility only on the basis that if an organization adopting a scheduler, whether or not it's Mesos, whether or not it's Nomad, whether or not it's Kubernetes, will not instantly solve your problems. No matter what anyone tells you, it simply won't immediately solve your problems. As Kamal mentioned in the keynote, not only will it not solve your problems immediately, it will probably solve some problems, but then give you a whole new set of problems. And specifically, what this allows, specifically, if you automate everything, you can leverage much higher utilization within the data center, and you would literally need to automate everything. And we'll be talking about, more about that in a minute. But a reason why is that even useful? Why do we care about utilization? So if you're running a fairly small infrastructure, 200 or 300 nodes, your overhead is fairly small. If you're running thousands upon thousands upon thousands of nodes, you suddenly care about electrical. A percentage point on your electrical bill is a huge amount of money. You care about cooling. You care about lots of large-scale operations things that you just don't care about if you're running a much smaller infrastructure. And so this is kind of a big driver as to why driving higher utilization within the data center and getting better utilization out of the hardware you have is incredibly attractive. So obviously, can't go without saying containerization. It's been mentioned several times already today. I'm sure it will be mentioned many, many more times in the next couple of days. But after many sort of frustrating years with RPM files, deb files, God forbid zip files, people moving stuff around for deployment, for that sort of development deployment relationship, Linux containers kind of offer us a path to, essentially make that more opaque for the operations team. This is really key in one of the systems I'm going to be talking to you about today. And so just want to say that this is a big trend. It's been around for 10 years, and it's really awesome to see that there's actually tooling that we can now use and actually roll out with a much bigger team without having to know an awful lot about the inside of the Linux kernel. The obvious trend, obviously, has been that it's been NoSQL everywhere. Except with all those places, we still want to do range queries because we still want range queries and reporting. So this is kind of super interesting from an operations perspective. if I put my developer hat on for a second, often I find myself wearing different hats, sometimes development, sometimes operations, sometimes just the complainer of all the things. But generally speaking, from a development perspective, it's enabled me as a developer to choose different tools. I can choose, say, for example, an index document store for a specific search use case. I can choose a big table, whether or not it's Cassandra or so on and so on and so on. Many different products coming to the market in the last 5 to 3 years, and so this has kind of enabled developers to solve specific problems. What it has done for operations is exponentially increase our deployment surface area. And so this is kind of an interesting problem because, as it turns out, it doesn't matter what product it is. It's not a comment on anything particular. It's just that, most software has just kind of got a real problem, and it's just, until you kind of actually run it at scale, you don't necessarily know, what the edge cases are for that thing. And so, getting that experience is something that it takes time to do, and it's just from an operations perspective, it's really it's hard. And so I'm going to be talking a little bit about this, about the sort of relationship between operations and development, and why we make choices, and sort of this kind of blends nicely into our observations. So, what have we observed over the last few years as we've been doing these things? So we've observed that infrastructure engineering is kind of unlike many other areas of engineering. The things that we build, they're typically used by many, many teams. So there's this kind of interesting cross-cutting concern. It's not like if I built a service and I acquired some technical debt in my service, and I can just refactor it and roll out a new version. If I've actually got something in the infrastructure that sucks, probability is I'm going to have to maintain that for at least 3 to 5 years. So, we have to be very careful about what we do. And so, subsequently, I would propose that 60% of what we do is actually social. We have to figure out what people want and why they want it, because a lot of the time, the things they want, they actually only want them because it's a crutch or a missing process for something they're actually trying to solve. So it's not necessarily presented with different options, they may not actually want the thing they actually think they want. And so this is actually a really kind of interesting point. So one of the things we always try to focus on is enabling sociological change within the teams. Any technical changes we make, they're basically an implementation detail. Because what we realized over time was that what we're really doing with the tools and the automation that we build with systems, they're actually changing the way that people work. And so this is something we're going to be covering in much more detail in a minute, but it's been key to how we've actually managed to progress. So I also want to propose that the operational complexity that we have is only proportional to the developer responsibility. So when I'm talking about responsibility, what do I mean? I don't necessarily mean that the developers are on call and stuff like that. I mean, there is an aspect of that, but I'm not talking about responsibility. Like, generally speaking, most people, they want to do the right thing in every organization. Most people are not bad actors. So I don't mean responsibility in that sense. What I mean is, the responsibility kind of runs deep in the sense that everyone in the organization has a shared responsibility for operational excellence. It's not such that if I'm a developer and I build a service, for example, and I deploy a service that talks to another service, and I assume the network is always going to work. Simple things like that. They have to be responsible and make sure that they plan for failure, that they don't add new things to the stack because it's cool, that they add new things to the stack because it's actually needed and solves a pain point. And so any complexity that we have operationally, is usually, and not always, don't get me wrong, like I was mentioning, much software is a sort of tire fire, so that there's a big problem with that in general, but sort of specifically, we want developers to be responsible and feel that they are operationally responsible for the things that they make. Which kind of leads us on to an interesting thing, which is that there's this interesting impedance mismatch between sort of the business staff who kind of value flexibility in what we build. So for anything that, whether or not you're a developer and you're building some service or job or some feature for a product, or whether or not you're infrastructure engineering, they will always want the most flexible thing. And as it would turn out, from an engineering perspective, you basically want the complete opposite. Because any flexibility that I have in my system, or perceived flexibility, usually means I've traded something off. So, for example, if I have an extremely flexible system that can answer queries in a multitude of different ways, probability is that thing won't scale. So it's like constraints enable us to do different things, and we'll be talking about this just in a second. But this kind of impedance mismatch between business versus engineering, we're constantly trying to find a middle way with this. Find a middle ground between what's the right amount of constraint, and internally we like to refer to this as the minimally powerful solution. And so one of my colleagues had this very interesting insight when we were working on a project together last year, which is that constraints liberate and liberties constrain. And so that kind of sounds kind of counterintuitive. And so I just want to present a kind of example just to try and get you to think about what that actually means in practice. So choose your favorite sport, whatever it happens to be. Let's say like baseball. In the case it's baseball, imagine if you had never ever seen a game of baseball and you were presented with all the bats, all the balls, the correct number of players, all the things that would necessarily be used during a game of baseball, but you had absolutely no idea how it was played, and you were asked to say, please construct a game using these materials. The probability of you selecting, so that there was one pitcher and one batter on the field at any one time, is not particularly high because there are many different, many different components, and so you can kind of imagine that. If we look at this from in this frame, what we can consider is that by giving them a simple rule like you can only have one batter on the field at any one time, or one pitcher, for example, then it allows the players to focus on other things. For example, like what is their batting technique like? What is their fielding strategy? So on and so on. And so if we translate this to software, what we find is that having constraints enable us to do things. They don't restrict us. They're actually empowering. And so for a larger company or someone or is an entity that's trying to scale large services, typically what we do is we want the minimally powerful solution that's constrained in all the ways that we need to solve the problem for today. And so that's not to say we don't plan for the future. We do, but it's a case of making the right trade-offs. Every single decision we make is some kind of trade-off. And so embrace that and kind of really understand that the constraints can liberate you. Despite what the business may say. So, I want to talk about a little bit of brief history. Where are we at? How do we actually get to this? Get to where we are today? So, if we wind back 4 years ago, we had a very different system. It wasn't particularly great. We had a pretty typical centralized configuration management system. It was very unmaintainable, but the key metric is that it roughly took us about 2 weeks to get from code complete as a developer to deployment. This is probably a pretty familiar story for anyone working in a large enterprise. There's a lot of bureaucracy, there's a lot of checking, a lot of balancing, so on and so on. But the key insight that we had was that from a development perspective, there's actually there's a non-existent relationship between operations and deployment. It's just non-existent. What happens is that as a developer, you would have had to basically walk over to operations and be like, hey, you know what? I just built this new service. And by the way, I need XYZ system libraries. I've got this configuration file, and that's kind of very high friction. And so subsequently, it was one of the slowest parts of our operation, and caused inordinate amounts of just lag basically in the general program. So if we wind forward to 3 years ago, which seems like an awful long time at this point, we basically generated this whole new deployment pipeline. It's primarily built on HashiCorp Packer, and it worked pretty great. We've done tens and tens of thousands of deployments with Packer at this point, and it works great. But the key insight that we had was that we changed the relationship. So we changed the relationship from basically pushing things onto the developers to say, hey, you know what? You can't be completely reckless with the choices you make. In order to make your systems more reliable and actually make them work deploy to deploy, make them more deterministic, we want to basically enable them to have any provisioning they want, and so the contract became, you need to deliver an RPM file and 2 YAML manifests. And so these YAML manifests, one basically explains how to provision the system, so typically that's basically just install the RPM. In other cases, they did some other funky stuff. Maybe they need to tweak some config that was a system config or something. But anyway, the point is it enables them to do that. And the second one enables them to define how the system should get launched. Now, this works pretty well, actually, it turns out. As a slight sidebar, it is amazing how creative people can be when you give them a fairly powerful solution. So people would come up with all sorts of interesting workarounds for things that they wanted to do. But the key metric here is that code complete went from 2 weeks to 40 minutes. And so from a business perspective, we've literally shaved weeks off of what we were doing. And so massively enabling, allows us to ship more and more product than we ever had before. And it was sort of a really, that was a really wonderful thing at the time. So, wind forward to today, and then people have kind of completely forgot that it took 2 weeks to deploy, and now people are kind of like, 40 minutes? I have to go and get a coffee? And so people, people are never happy with any of the things you build, So I'm sure many people can relate to that. So where are we right now? So we have invested a significant amount of time in basically taking the lessons we learned whilst building a previous system, and try to codify them into a sort of a holistic centralized system that will handle all the orchestration for deployment. And the key metric here, code complete from 40 minutes to less than 5 minutes. And so in the common case, it's like a couple of minutes. So that's really, that's very, very enabling. And so one of the things, I'll be talking in detail about how this is structured and what we actually did with it. But we ended up adding lots and lots of interesting things here, like application dependency management. So the system knows if you have service A, service B, service C, it knows that A depends on B, depends on C. And it knows about all the versions that are deployed, which enables it to actually reason about the topology of the network. And so, we affectionately call this system Nelson. We got Travis, we got Jenkins, so now we got Nelson. And why is it called Nelson? So Admiral Nelson from the Royal Navy. I'm British, so yeah. As an operations person, I'm sure this quote speaks to many of you. Your pager goes off at 2 in the morning. They're absolutely desperate affairs, and they're absolutely desperate remedies. So what were we trying to achieve with this thing? Now, I guess in some senses we had kind of a lofty kind of what we were going to do was going to be a beautiful new day. And so we realized that system elements within our system should be awesome at just one thing. And so I just mentioned Travis. We migrated from Jenkins to Travis, and sort of the realization there that Jenkins is actually discretely too powerful. It can do anything, and that's actually a problem. And so we wanted to constrain the system in different parts, and I'll be showing a workflow diagram in just a second. We'll talk about more about that. From an operational responsibilities perspective, developers are on call, like second line, and what it allows them to do is it allows them to basically break it, you bought it. You're on call, second line. If you get paged, it means that there was the operations team couldn't remediate the issue that you had, let's say at 2 in the morning. So pretty standard model. We want to drive them to be more responsible, and we want to enable them to do the right thing. So my team specifically provides a bunch of libraries to them. So whether or not it's, say, for example, for circuit breaking or discovery and many other things. We provide all these things as libraries, so that it's like we give them the building blocks for each different part, and that they have to assemble it in a responsible manner. But we wanted to focus on orchestration, not on placement. And so specifically, Nelson is responsible for orchestrating the deployments to all the different data centers, as opposed to, it's not a scheduler. It's discretely not a scheduler. It could be implemented on top of a scheduler. It isn't right now, but it could easily be. But yeah, so we'll be talking about this nuance in a second. So one last thing. Manual access, any manual access, that's not a thing. So they have to have awesome logging. We provide libraries and convenience for that. They have to have awesome monitoring. Same deal, libraries and convenience for that. They have to have, they have to meet a certain bar of sensible things. Because if it's not there, they're going to get called. So, how does it work? So, this is pretty common. We've seen this chatting with other people the last couple of days about what they've been doing and as other large enterprises, what are the kind of concerns they have. And so it turns out that actually many people have this problem. And so internally, we operate like an open source development model. So we have GitHub, we have Travis, and we have Nelson. So Travis is awesome at builds, awesome. GitHub is awesome at source code, or source code management. And so the goal is that Nelson will be awesome at deployment. And so that's the hope anyway. So internally, all code before it gets merged to the main line has to be pull request, peer reviewed, pick up any problems. all pull requests are built, so they get feedback about code coverage and all the other things. So it gets merged to master, then it gets sent to Travis for a build. Travis does the build, publishes a Docker container to like a staging repository. Then Travis notifies GitHub by basically creating a GitHub release. And once the GitHub release is created, we kind of have a tag, and we have a tag and all the release notes and everything associated to that release, including basically a small manifest which says, hey, this is the Docker container, this is all the way it should get deployed, and then GitHub then uses webhook on GitHub to basically go and let Nelson know, hey, we've got a new release, you might want to do something with this. And so Nelson's like, hey, cool, new release. And what it does is it then basically goes through sort of a set of specified workflows. We'll talk about that in just a second. And then it does container replication. So Nelson can basically replicate. So from its staging Docker repository, it will basically take all of the various pieces and replicate them to multiple remote data centers. So what kind of things can we deploy with Nelson? We have this concept of units. And so a unit is just kind of some unit of work. Fairly typical thing. We have jobs. Jobs can either call services, or they can basically just be a standalone job. Maybe they're chewing on a few petabytes of data, whatever, right? But the thing is that they are ephemeral. They typically run on some kind of schedule, and they could be one shot. They could be various different things. As an interesting side note, you see commonly in most schedulers that, like, whether or not it's Kronos, whether or not it's Nomad, that they give you fairly powerful scheduling semantics. Like Nomad gives you cron, Kronos gives you ISO 8601. These are actually very powerful things. You can do anything with them. And so kind of fitting into our sort of policy of like to have the minimally powerful solution, it actually turns out most developers don't want that. They want to run like half hourly, they want to run quarter hourly, or they want to run hourly, or they want a one-shot job, or they want it to run monthly. And so there are the options. And so we constrain the users to a subset. And so when they define it in their manifest file, super simple, not much to explain. How many times should we try it? When should we schedule it? And they just supply a little bit of description. And they say, OK, this thing depends on this other thing. And they supply a version. We'll be talking about that in just a second. Services, basically the same deal, except they can bind to a port. And they can optionally mount volumes and things like that. But the key thing here is it's basically the same. It's basically the same thing. It's just another unit, some unit that will be passed to a scheduler replacement engine, and it will get deployed in a data center. So pretty much the same deal with the addition of ports. We'll be talking about expiration policies in just a minute. Note that they can also have dependencies, and you can have multiple service components that can depend on multiple other service components. Now, this is kind of where it gets a little bit interesting. So for anyone who's done any work on resource managed clusters, you know that if you want to expose external services from within inside the cluster, that is kind of tricky because naturally the services could be arbitrarily moved at any given time and essentially wouldn't be on the same IP. And then you've got kind of all these interesting discussions around, okay, I needed to deploy something, but actually my network is like, it's not a flat network, so I've actually got it on, only got all the IPs of my slaves or any workers, and I'm doing port remapping, or you could have a flat network where every container has like, its own discrete IP, in which case it's like, well, I need to expose one external IP, and then, and all this kind of stuff, right? Because you need to map to DNS and so on. So we have this specialized case, which is called an edge proxy. An edge proxies basically allow you to integrate with the internals of the other things within the cluster. You can basically say, OK, I want to expose this particular port, give it a name, say we're going to expose it 443, let's say it's HTTPS, and then you say, I'm going to depend on this other service. And so basically the proxy just becomes sort of this like fix-it point on the system, and now depending on which provider you're deploying into, so if we're deploying into our own environment, we have some specialized networking stuff that handles that, and if we're deploying into, say, AWS, we'll spin up like EC2s with ELBs and all that kind of thing. But the system knows about that. And that's user selectable, so the user has to know where they want to deploy or what kind of resources they would want, and they can specify that ahead of time. So this is an interesting edge case that anyone who's kind of worked on this will definitely resonate with. So I kind of skimmed over it earlier, but where are we at with what does Nelson actually do? So specifically, when GitHub calls Nelson, Nelson will execute a workflow. Now there are multiple like predefined workflows, and we kind of have this interesting insight that every single data center it's just a failure domain. Now, it doesn't matter whether or not it's if it's, say, I mean, more people are probably familiar with Amazon. If it's Amazon, then you can think of a failure domain as being like a region. If it's their own data centers, well, they're electrically redundant, so one data center kind of equates to one region. And so from a Nelson's perspective, it has multiple different failure domains. And with the way we treat it is we basically treat every failure domain with its own registry, with its own console, with its own scheduler. So right now we support Nomad or Mesos, and with its own Vault. And so this allows us to operate in such a way where we have complete redundancy. So if we have a failure in one data center or in one region, we're not operably impaired in any of the other regions. So that it can pull containers. The scheduler can pull containers from its local registry. We can still do discovery because hey, we had its own console. And so console for us, Nelson, when it's executing its workflow, is actually executing multiple different things. So when it talks to console, it says things like, hey, user specified XYZ alerting rules and these thresholds, and it basically transfers all that into the console. And also, and not just for health checks, by the way. So for probes on console, I'm not talking about that specifically. We have a whole bunch of integration with other monitoring systems. And so what that is it's basically it allows the user to express a set of rules, and those rules get translated into the monitoring system used in that database, in that data center, sorry. We also use it for discovery. So we make heavy use of console service catalog. Like I mentioned earlier, we also provide a set of libraries to make this kind of super useful, super convenient for users. So we're a JVM shop, so we're using Scala. And we have a whole set of very nice libraries that kind of have a functional approach to doing discovery. There's a lot of interesting details on the routing, but I probably won't talk about that unless anyone wants me to. So scheduling. Scheduling for us, again, is just another implementation detail. It's how do we wish to manage the resources within those data centers? And so a lot of this is because we realize that no matter what we do, we will always be wrong. Like if we choose Mesos today or we choose Nomad today, like a year from now, it might be something else. So kind of owning the relationship with many hundreds of engineers is actually kind of expensive. Changing that is high friction. So Nelson becomes this kind of a thin layer between us and the data center scheduling. So Nelson is specifically not interested in placement. It's specifically not interested in the runtime. All it's doing is orchestrating metadata, asking the scheduler to do things, and then the scheduler will figure out how best to do placement, what resources are available, where does it make sense to fit this thing in. And so that's a really key point. Like, Nelson is not a runtime system. Likewise, if we have an outage of Nelson, then the only thing we're impaired to do is basically do new deployments. We bring Nelson back up, and we're good to go. Credentials. Vault, it was talked heavily about in the keynote, makes total sense, very reasonable. Yeah, not too much to say about that. So the lifecycle part. So when we were in our second system with the Captain Picard, we had this very interesting insight, and actually, it was less an insight more than it was just a huge mistake. But we. Often those things are the same, so sometimes it's tough to tell them apart. But we had this we realized that even though we had massively enabled the organization to go from 2 weeks to 40 minutes, what we realized was that we actually didn't plan for cleanup at all. And I'm not just talking about AMI sprawl, which some people are probably familiar with. It's just that you're consuming large quantities on the cluster, whether or not it's, and I use Amazon analogies so everyone's on the same page. You've got load-bound EOBs, and you've got kind of you've got instances lying around, and you've got stuff that the developer started that they didn't tell anyone about, and it's just this, you've got stuff in the cluster that you don't know why it's there as an operations person. And you have to kind of go hunting around, and you're asking this constant question, do we need this thing? So this is kind of where we decided to build a holistic lifecycle management system. So from a lifecycle perspective, you can kind of consider that there are multiple discrete states. And so any given service, this is particularly pertinent for services, but all units go through this process. There's a pending stage, there's a deploying stage, then it gets warmed up. If need be, often it's skipped. and then it goes active. And so users can then basically, there's sort of one use case, which is where users, if I own the foo service, I may not want anyone to use like the 1.0 version of the foo service because there's a 2.0 version of the service. So I can actually go in there and deprecate it, and then any new deployments against the old one get flagged, and then they basically get like a time which they set, on which case as a user of the foo service 1.0 that I have to then go and upgrade to the 2.0 service. So it's basically a way of pulling up the short tail, pulling up the long tail for basically phasing things out. Once it's deprecated and once it's sort of past its expiry time, it goes into the garbage state, and then we have a reaping process in Nelson that will just go and clean everything up. Now this is sort of where it gets interesting. So imagine we have a more complicated graph. For services, this is kind of really interesting. So, and this is a complete simplification. We have hundreds upon hundreds of services, and that's just logically. So by the time you consider that you've got multiple environments with multiple graphs with thousands of deployments, like your graph is actually kind of big. So you end up in this kind of awkward problem. So let's say that we take the 6 service, for example. And now I look at it, I realize this is a terrible way to speak about it because you're 6 1.2, which is kind of a little bit. Anyway, whatever. So let's say that you had a 1.3 version of the 6 service, and Nelson will automatically bleed the traffic from one to the other. So we basically rely on the protocol can't change. So basically, if the developer made huge breaking changes, then they haven't honored their contract, and we'll be talking about that in a minute. But we bleed traffic from one to the other. Upgraded, awesome. They've removed the dependency on the 7 service. So then Nelson can come in and be like, hey, well, it looks like there's actually no users of this 6 1.2 service or of the 7 service. So you know what, we'll just prune the graph. And so Nelson is basically looking at the entire runtime system versus what the kind of topological graph it knows about and all the dependencies, and doing automatic graph pruning. And this is sort of really awesome. So Nelson has a whole set of policies, and so we skated over it earlier, but this concept of like an expiration policy is actually a really killer feature. Because you, as a developer, you can be like, there's no case that always works. Like if you're just dealing with services, it might be okay to say, you know what, just keep the latest. But then you get these edge cases around people like, well, we were doing this data migration and it was sort of not really compatible, so we had to roll out a new version and we need both of them. And all these edge cases. And likewise, with data science, this crops up constantly. If they're running multiple models, they will typically want to keep, say, the last 2 or 3 major versions of different models because like the last major model was good versus the new one. And so there are many, many different like nuanced cases. So we basically provide a suite of expiration policies and say, you know what, you can choose how and when you want this thing to be cleaned up, but it will affirmatively be cleaned up. Nothing can last forever. So you're always living on borrowed time. That's the way we position it with the development team. So they just need to determine for what value is it borrowed. So like I mentioned earlier, this kind of eliminates the need for, do we still need this? Which kind of comes up constantly. Particularly problematic when you're running on a fixed set of resources because you run out of machines. So just some sort of, when I finish up with some conclusions or sort of overview. It is absolutely imperative that you automate everything. Like button clicking and approvals and all that stuff is not the creative, intelligent work that the human brain excels at. So don't bother with that. Automate everything. Your future sanity will thank you for it. You should persistently question any manual process. What you'll find the majority of the time, particularly in larger companies, is the manual process is an organizational crutch where automation or tooling is lacking. So your integration points in large systems, or large teams indeed, are usually highest cost and the highest friction. So typically you want to prefer machine verifiable protocols, i.e. not JSON, where you can. You want to use polymorphic type systems, you want to use binary wire formats, but you want to realize the importance that the teams working together, they also form kind of a soft protocol. And so if one team has a dependency on another team, they not only do they have a physical technical contract, but they also have a social contract, which is that person A is going to be really upset if person B doesn't honor their contract and they continually roll out breaking changes when they said they weren't breaking, for example. So those soft protocols need evolution and maintenance, just over time, just like the code base does. So if your organization or team is going to be successful, there are a few things you need to do. First thing you need to do is listen a lot. As infrastructure engineering, we do more listening probably than we do talking. We do a lot of learning, and we're most open for criticism. And so that kind of cuts both ways. If we're giving criticism to the development team, infrastructure engineering staff need to know how to give criticism objectively, and also how to receive it, because we're not perfect either. We make a lot of mistakes, just like everyone else, because we're human. And I want to sort of also say that you should never ever settle for tools that are mediocre. It never makes sense. If you're using a tool and thinking, well, this is really mediocre, I think I could do better, understand that there's a trade-off between buy versus build, but if you truly can't buy it, then don't be afraid to build it. For example, up until about 8 months ago, building all the reduction in deployment time, even though I was working on it for the last few years, it wasn't even my main project. It was a side hustle. So it's like the thing there is that if you work in a small company, maybe you're a 10-person startup, use hosted solutions. Enable your organization to get things done, by using those hosted solutions if they work for you. If you're a multinational megacorp, prototype often, demo often, show that you can make change. So in the case of the 2 weeks to 40 minutes to 2 minutes, that wasn't even my main job. It annoyed me to the point of having to fix it. So you can make change even in large companies, and a single person can have a huge impact on any organization, big or small. So we live in a world, particularly with the tools, the HashiCorp tools, and other similar tools that are in the market. We have the ability to change many, many things, and one person can be incredibly impactful. So with that, I want to thank you very much for listening. If any of these things are interesting to you, we're hiring. Simple plug. But the other thing I'd also be interested in feedback in, some of the other people that we've talked to said that they would be interested in using Nelson. So if any of this does sound interesting, or your organization has similar problems, we'd love to hear about it. It's something we might consider open sourcing in the future, but we don't have any plans to right now. But I would love to hear about it if this is kind of interesting to anyone. Anyway, with that, thank you very much for listening, and it's been a pleasure.